Describing reactions in aqueous solutions. We've learned a little bit about equations, so we're going to learn about chemical equations. We're going to learn about some more chemical equations. There are actually different types of chemical equations. One is a molecular equation, and this is what we think of as a regular or normal equation. A molecular equation is going to show the complete formulas for all the reactants and products. And this is the sort of equation that we've been using so far. And so this is an example of a molecular equation. It shows potassium chromate in aqueous solution reacting with barium nitrate that's dissolved in water and is aqueous. And that reacts to form barium chromate, which is a solid, and potassium nitrate, which remains aqueous. So that's useful, but it doesn't give us a clear picture of what's actually going on in solution. So a complete ionic equation can be useful. In a complete ionic equation, all of the strong electrolytes are shown as ions. So let's just review what a strong electrolyte is. A strong electrolyte is an ionic compound that dissolves and dissociates completely into ions. So when you put potassium chromate in water, it's soluble. You actually don't have any potassium chromate molecules or anything. You have potassium ions and you have chromate ions. So in the complete ionic equation, we're going to show the species as they actually are. So the potassium ions have separated from the chromate ions, and so we're going to show them separately. And the barium nitrate is separate. Now these equations tend to get a little bit long, and so sometimes you have to bump them onto two lines. So put the arrow up here and then put the rest of it over here. Sometimes that's just the best you can do. In the products, the barium chromate formed the solid. This is that reaction we talked about earlier where the clear solution and the yellow solution made the yellow solid. So this is a solid. Those are together. We don't write those ions separately. But the potassium nitrate was soluble. That was aqueous. It was dissolved. This is also a strong electrolyte. So any ionic compound that has aqueous behind it is a strong electrolyte. And so when we write the complete ionic equation, we're going to show the individual ions. If the state symbol there is solid, liquid, or gas, then you keep it together. So when we look at this equation, here it says, notice, we have two potassium ions here and two potassium ions over here. Nothing really happened to the potassium ions. They were there mingling at the party, but they didn't get involved with anybody. And the nitrate ions, likewise, unchanged before and after. Nothing happened to them. The chromate and the barium did change because they came in as aqueous ions and they left as a solid. So something happened to them. They got involved. We call those ions that nothing happened to spectator ions. So you go to, say, a boxing match, and you sit in the stands. Do you leave with a black eye and a bloody nose? Not unless things got really out of control in the audience, right? No, it's the guys in the ring that get beat up. They're beating up each other. The spectators are just sitting around watching the fight, right? So in this equation here, chromate and barium are doing something. Potassium and nitrate are just watching, and so we call them spectator ions. Nothing happens to them. So those are spectator ions. They don't participate directly in the reaction. So then we also have a net ionic equation. So if you've ever gotten a paycheck, you know that there's a difference between your net pay and your gross pay, right? Gross pay is always a bigger number, and the net pay is smaller because they took out taxes and Medicare and FICA and all these other things, right? The net pay is what you actually get to take home. The rest of it they sent off somewhere. In a net ionic equation, we're only looking at the stuff that gets changed. So basically, we're ignoring the spectators. So any of the spectator ions from the complete ionic equation, we're just going to leave those out. and we're looking, this is the net ionic equation. This is what's going on in the boxing ring. This is what's changing. Barium ion is reacting with chromate ion to form a solid barium chromate. So we don't show we don't show the spectator ions. We're only showing those things that actually undergo a change. The nitrate ions and the potassium ions were there, but they didn't actually undergo a chemical reaction. They are unchanged. The barium and the chromate underwent a change, a chemical change. So let's do one. Write the correct molecular equation, complete ionic equation, and net ionic equation for the reaction between cobalt-2 chloride and sodium hydroxide. So I would not make you do a problem like this by yourself on an exam. I would break it into pieces, but in lecture, as a demonstration, it's really useful, demonstrates lots of things. Okay, so we've got to write equations, and we've got two reactants here, cobalt-2 chloride and sodium hydroxide. We need the formulas for those. So I'm going to go up here to save myself a little space. Cobalt-2 chloride, what kind of a compound is that? Ionic, covalent, or acid? It's ionic. So cobalt-2, that Roman numeral clues us in. Cobalt-2 is CO2+. And chloride is chlorine, and what charge does the chloride ion have? -1. So then the formula for this is COCl2. And then the other one, sodium hydroxide, that's also ionic. So sodium is in group 1, it's got a +1 charge. Hydroxide is something you need to memorize or look it up in a table. We've got +1, -1, all we have to do is put those together. That's sodium hydroxide. Those are the reactants. So first we're going to write the molecular equation. So we're going to have cobalt chloride, and we're going to need state symbols in here, and we're going to have sodium hydroxide. I'm leaving a space there in case I need to put a coefficient to balance it. And these guys are going to react. How do we figure out what state those are in? The question is a little vague. It should say that this is happening in solution or something like that. You can't really get a reaction between two solid ionic compounds. You need to dissolve them in water. We could look both of these up in the table or the solubility rules, and we see that chloride compounds are generally soluble. Cobalt's not an exception. And so this one is aqueous. Sodium compounds are generally soluble. Actually, they're all soluble. And so we get aqueous there. They don't tell us what the products are. So on Monday we learned about reactions that form a solid, and what we do is we see what happens if we swap the partners. So here we have our reactants. Now, just as kind of showing your work, I'll maybe make that a different color. Under here, I'm going to write these guys with their charges so I can see who the players are here. I've got cobalt-2 ion and chloride ion. Over here I have sodium ion and hydroxide ion. So what we're going to do is we're going to have these guys swap partners. And those will be the products. So cobalt came to the party with chloride. Cobalt's going to leave with hydroxide. Sodium came with hydroxide, but he's going to leave with chloride. So over here, I'm going to just write them with their new partners, and the order doesn't matter. If you put the sodium and the chloride first, that's fine, because 2 plus 3 is 5, and 3 plus 2 is still 5. It's just adding. Order doesn't matter. So those are our new couples. And then we have to look at the charges to see how they're going to go together. Cobalt plus 2 and hydroxide minus 1. We're going to need 2 of the hydroxides to balance the charge there. So the formula for that guy is going to be COOH2. And we're going to need a state symbol. And then over here, we've got sodium and chloride plus 1 minus 1. All we have to do is push them together. And we should put a state symbol in there as well. Now that one you might know. Is sodium chloride soluble in water? Yeah, it is. That's table salt. Okay, you're making spaghetti, you sprinkle salt in the water, what happens? It dissolves. Sodium chloride is very soluble in water. You could also look it up in the rules. Cobalt hydroxide. Well, if we look that up in the rules, solubility rules, we find that most hydroxides are not soluble. And so this is going to form a solid. So now we have all the formulas in our molecular equation. Is this equation balanced, though? No, it's not. So let's check it out. Over here, we have 1 cobalt, and over there we've got 1 cobalt. So that's okay. Here we've got 2 chlorines, and over here we only have 1. We can fix that by putting a 2 there. Now, did that mess up the cobalts? No, that didn't do anything to the cobalts. It changes the sodium, but we haven't checked out sodium yet, so we're okay. So we've got cobalt and chlorine fixed up, and then we're going to look at sodium. Here we've got 1 sodium, and here we've got 2. So that means we better put a 2 over here. So now we've got 2 sodiums and 2 sodiums. That changed the hydroxide, the O and the H, but we hadn't fixed those up yet. So now we've got cobalt, chlorine, and sodium all balanced out. Let's check out this oxygen. 2 oxygens here, and it's not found anywhere else. Over here, we've got 2 oxygens. So the oxygen's okay. And then the hydrogen is the last element, 2 hydrogens, 2 hydrogens. So there's our balanced molecular equation. Any questions about that one? Pardon me?
Do you have any other products besides those?
No. No. When you have 2 ionic compounds like this, the only thing they're going to do is switch partners.
What can we have, like, put 2 cobalts and a bunch of hydroxides with 1 sodium, or?
No. No. There are. We lied to you in Chem 10, or I lied to you.
Okay.
It's for your own good.
Okay.
There are ionic compounds that are more complicated. Alum is one. It's got aluminum and potassium ions with a cation. I'm sorry, with an anion. And we haven't talked about that, and we're not going to talk about that. So there are some more complicated things that go on, but we're just going to stick to the simple ones. But these 2 compounds together, that's all they're going to do. Yeah. And that's one thing that I find nice about chemistry is a lot of it's predictable. Unlike real life, children are not very predictable. I guess you could predict that they're unpredictable. But they want to do this, and they want to do this, and they want to do this, and then all of a sudden when you really need them to want to do that, then they don't want to do it anymore. It's like the cat. They always want to be on the other side of the door. But the chemicals, they just always do the same thing. I love it. This is predictable. So it's like simple math. 2 plus 2 is always 4. It's just nice that way. So there's writing the molecular equation. Doing something like this involves a lot of little skills. And you have to put them all together. And so overall, it can be pretty challenging, especially when you're first learning all these individual things. Combining ions and balancing things, okay? But it can be learned, okay? So it's you know, this is not differential calculus or anything, or multivariable calculus. I mean, that's kind of, I didn't even really like that much. But this is just learning to think about some things in a slightly different way. It's very simple math, counting and multiplying by small whole numbers. But it does require practice, and you gotta do the individual steps. Okay, enough of that. Okay, so now we want to write the complete ionic equation. And it really is helpful to have that molecular equation to go off of. Because what we're going to do is anything that has AQ, we're going to separate into the ions. And we already have our little notes here, so we already have the formulas for the ions. So we've done a lot of the work for this second equation already. So COCl2, that is two separate ions, cobalt 2+. We should put AQ after these, but it's not going to fit on the page, so I'm going to leave the AQs out. So we've got cobalt, and then we've got chloride. And if we look at this formula, there's one cobalt and there's two chloride ions. So let's just put a 2 in here. You could go back and fill those in later, but I think it's easier to do now. And then over here we've got 2 sodium hydroxides. That means we have 2 sodium ions and 2 hydroxide ions, because sodium hydroxide is aqueous. The cobalt hydroxide is a solid. That means it's sitting at the bottom of the beaker. It's not floating around, and so we just copy that one down as is. And then the sodium chloride at the end is aqueous, and so we write that as individual ions. So at that party at Chemistry Land, this complete ionic equation is telling us that cobalt and chloride and sodium and hydroxide were all mingling at the beginning of the party, but cobalt and hydroxide got pretty tight with each other and they went off and found a private place, and now it's just sodium and chloride mingling. These guys are stuck together. So this is describing what's happening. We took cobalt and chloride, which came in, dissolved in water. Sodium and hydroxide were dissolved in water. We had 2 solutions. When we mixed them, the cobalt and the hydroxide stuck together and formed a solid and fell to the bottom of the beaker. And the sodium and the chloride remained in solution. So this is our total ionic or complete ionic equation. If we pay attention to these subscripts and carry everything down, it will be balanced already. But we should always check. So here we've got 1 cobalt and 1 cobalt, 2 chlorides, 2 chlorides, 2 sodiums, 2 sodiums, 2 oxygens and 2 hydrogens, 2 oxygens and 2 hydrogens. And so it's balanced. In the complete ionic equation, because you're showing individual ions, the individual ions do have their charges. You can't put CO without its charge, because that would be cobalt metal, which would be a solid. It wouldn't be aqueous. Any questions? Once you have the complete ionic equation, writing the net ionic equation is easy in comparison. What we're going to do is we're going to look at this and see which ions are the same in the reactants and the products. So does chloride change? Here we've got 2Cl minus, and over here we've got 2Cl minus, exactly the same. So I'm going to cross those guys off. Nothing happened to them. They were spectators. They're just watching. They're still watching. What's the other ion? Say it louder. Na, sodium. We got 2 sodium ions in the product and 2 sodium ions in the reactant. Nothing happened to the sodium. It's still just swimming around. So then to write the net ionic equation, we just copy down everything that we didn't cross off. I'm going to put the AQ state symbol back because now I've got a little more room. 2OH minus, and that forms COOH2, which was a solid. So that's our net ionic equation. What this tells us is that the sodium and the chloride really don't matter. If we had potassium in there instead of sodium, this reaction would proceed exactly the same. If we had bromide in there instead of chloride, it'd be the same thing. The identity of those guys really didn't matter. The boxing match, okay? Who's in the ring? The people in the ring, that matters. Does it matter exactly who's in the stands watching? Nope. If so-and-so didn't come up and gave his ticket to somebody else, does it really matter? No. Now, if one of the boxers gets somebody else to come for him, then things are going to be different. Any questions?